Hi everyone, in this episode we're going to take a look at standing waves. What are they? How do you make them? What are the equations governing them? And what do we mean by modes of vibration? So let's get started. Okay, so I've got a little simulator up. This is a standing wave simulator by Nerd Island Studios. Check out their website here. This is not my own work, but it's a useful little demo. So if we have a blue wave progressing from the left to the right of the screen, I'll follow it with my cursor just so you can get your eyes trained onto it. Watch a crest and you'll see that it's traveling from the left to the right of your screen. That's very interesting. We've got an uppy downy wave. It could be a transverse wave. It could be a longitudinal wave, because all we're looking at here is we're looking at displacement on the axis over the course of a period of distance or time. Okay, so that's a blue wave going from left to right. We'll hide that for a second, and let's have a little look at a little orange wave, which is traveling from right to left. Check out one of the crests on it, and you'll see that as you track it, it's going from the right-hand side of your screen across to the left-hand side of your screen. All right, so that's cool. Let's imagine that these two waves meet each other. Well, then we have our blue one, if we try and just focus on it, traveling from left to right, as it was before, and our orange one, which is traveling from right to left. Except that now your eyes aren't quite tracking them the same way, are they? They're looking a little bit more in the uppy-downy direction, and that's because superposition is a thing, and the superposition rules still apply to two waves arriving at the same point, and that is that the overall displacement caused will be the vector sum of the displacements at that point. So these two waves will not be observed. Okay, what will be observed will be the superposition of these two waves, but the superposition of these two waves isn't going to be a static thing. It's going to oscillate because these waves are oscillating. So let's have a little look at some of the more simple points here. For example, what we see is that these two waves seem to always be locked in place together, which means that the superposition of these two is always going to add. That means that if the amplitude of a wave that's blue is 2 squares and the amplitude of the wave that's orange is 2 squares, at the top of this peak here, we're going to end up with a superposed amplitude of 4. At the bottom here, we're going to end up with a superposed amplitude of -4. And as a result of that, we're going to get these huge twists and turns in here. Okay, these are called antinode positions, and that is that they are the maximum distance that you can get away from your rest position. Okay, if we come across a little bit though, then we have other situations like here, for example. Here's a bit of a weird one, that sometimes the waves are crossing and sometimes they're not. But at any given time, it appears that when the blue wave is in the positive section up here, the orange wave is in the negative, and vice versa. And the only time that they meet is basically as they cross through 0. Which means that if you were to take the vector position of those, or the superposition of those two situations, then what we would get would be that we would get an overall displacement of almost 0. Because the positive would cancel with the negative is going to cancel with the positive, and when they do meet, it's 0 plus 0, which gives you 0. This is called a node displacement, as in there is no displacement. It is called a node on your standing wave. Okay, so what do we mean by a standing wave? Well, if I actually pop in the superposition here of these two. Now remember, our blue wave is traveling from left to right, and our orange wave is traveling from right to left. So what we mean by a standing wave is if I put the superposition of these two in, what we can see is we get, as we said, we're going to get maximum displacement at these points, so our big amplitudes are here and here. We're going to get essentially no displacement at any given time here. That's not going anywhere. That's just sitting there all the time. Even though we've got waves going on, we have no overall displacement. Now the question is, what direction is this wave traveling? And this wave isn't traveling. You can't say it's going from left to right. You can't say it's going from right to left. It does appear to be sitting in one spot. And this is what we mean by a standing wave, that it has no definite direction of travel. The blue wave is still traveling from left to right, The orange wave is still traveling from right to left, but our overall resultant wave is not moving at all. And this is what we mean by a standing wave. Okay, so back to some theory then. How do we make standing waves? Well, standing waves are actually pretty simple to make. All you need is a system that allows for some degree of reflection. So if I have a wave, and I'm going to draw this really gently, so if I have a wave traveling this way, this is sketchy, but we'll get better in our graphics as we go on. If I have a wave traveling this way, and it is in some way forced to reflect back the other way, what we get is we get a reflection. And the points that meet here and here will form what are called node positions. That is that at any given time, as they oscillate, there will be no displacement at those points. So here we have what is called a node, as in no displacement. And at these points where we see the maximum displacements on both the incoming wave and the outgoing wave, our oscillation will travel between these two maximum positions, and these are called anti-node positions. They are the antithesis of node displacement, so these are anti-node positions. Right, now normally you just label these as A for anti-node and N for node. So we've got a standing wave. We want to see how do we make them. Well, we've got a couple of problems here because it's not just any little wave that can make a standing wave. What we need specific kind of circumstances. All right, so the most simple situation is where you have a string, and this string is set at a fixed position on one end to another. And think of a guitar or something along those lines. If we stretch a guitar string between the start and the end of it, then what we need to do to make a note is we need to pluck the string. And what will happen is that a wave will travel along here, bounce back off here, and we'll set up a standing wave. Now, there are a couple of things though. Because this position is fixed, the particles at this point are unable to move. So no matter what you do to this string, this must be a node. Okay? And at the other end, this also has to be a node because it has no displacement. So the result here is this is called the stretched string problem. And on a stretched string problem, what we end up with is we have a node at one end and a node at the other end. And then the question is, well, what type of situations can we get ourselves into here? And what are the possibilities for creating standing waves? Well, the most simple one is that we have just an arc like that, okay, that we pluck the string, and then there's a reflection backwards like that. So this point will oscillate upwards and downwards between these two, between here and here. That's a terrible drawing. So this point will oscillate upwards and downwards between these two positions as the standing wave is created. So this is our maximum displacement, but these can't move, and these will be somewhere in between at all given times. So we'll get this wave that vibrates upwards and downwards. This is therefore an antinode position. Okay, we get a node, an antinode, and a node. This is the simplest standing wave you can make. Now clearly you could make like quarter waves and all sorts of things, but if I attempted to do that, so say I plucked it in such a way that I ended up with a wave that looked like this, well then this isn't a node at this end, and therefore this isn't a stretched string problem. Okay, so this is the simplest wave that can be set up to make a standing wave on this. And because it's the simplest, we call it the first mode of vibration. Okay, in older terminologies, we sometimes call it the fundamental. And some textbooks still refer to it as the fundamental. Okay, this is the first mode of vibration. It is the fundamental mode of vibration. Now, what do I mean by mode of vibrations? Well, because we could set up a different standing wave. Again, we have a stretched string across here that started off as this little red one, and then we gave it a pluck in some way, in such a way that we set up this wave, which is that we've got the black wave was the one that we started up, but of course we got a reflection that came back like this, and the whole thing is repeating over and over and over again. So this position is vibrating between here and here. This one's not moving because it's a node. This one's not moving because it's a node. This is moving, but as it comes down here, this one's going up here. And the result is that at all points, at all times, this is also a node position. Okay, so we've now upped our level of complexity for our wave. So we've gone from kind of a half wavelength up here to a full wavelength up here, a full lambda up here. Now, because we've done that, we have now an antinode position here because we have this maximum displacement going on between here and here. That's an antinode. But we've also got an antinode here. Okay, so we should be able to see that this is a much more complicated wave system, but only by one node. All we've done is add a node in here. And as a result, we've had to add in an extra antinode as well. So instead of we went node, antinode, node for 3 points of interest in here, we now have node, antinode, node, antinode, node. And that's sort of a thing, that as you add a node into something, you have to add an antinode and vice versa. Since this is now the second most simple way that we can create a standing wave on our stretched string, then we have the notation that this is called the second mode of vibration. The second mode of vibration. It does have other names as well, but it's beyond the course of this scope. You'll sometimes hear it called the first overtone or the second harmonic, but this is not what we want to have here. Okay, this is the second mode of vibration. We're just going to use modes of vibration because that's modern and sensible and good. Okay, so we're keeping it with that. All right, onwards then to the third mode of vibration, which will be what we want next. So let's label that in already so that we know what we're talking about. And that is going to be the next most difficult way to do it. Now, how that's going to be done is we're going to add another node in here. And because we'll add another node, we'll add another antinode. And we'll end up with something that looks a little bit like this. As we can see, we still have our string. It's still the same length as it was at the start. We've just managed to pluck it in a way that is now generating a much more complicated wave. It is a full wavelength and a half. It's 1.5 lambda. And as a result of that, we've introduced an extra node. So there's a node there, and there's a node there, for a total of 4 nodes as opposed to 3 nodes. And we now have extra antinode positions as well. We have an antinode position there, we have an antinode position there, and we have an antinode position there. And this is the third mode of vibration. And the fourth mode of vibration would be to simply draw 2 full wavelengths along this line. Now notice that the frequency of these waves is certainly going up. But this was a half wave in a distance of L, say for the length of the string. This is now a full wave in the same distance, and this is now a wave and a half. Okay, so that's important in its own right. And we can actually work out what the wavelengths of these are if we know the length of the string. Let's take a look at that right now. Okay, so here we go. We've got our first mode of vibration, our second mode of vibration, our third mode of vibration drawn already for us on the same string. And let's assume that this string has a length of L. So this is L, length L from one end to the other end. And that's true for all of our strings. Then in the first mode of vibration, so this is our first, let's give that a number. Let's call that n equals 1. Okay, where n is the mode of vibration. So for the first mode, n equals 1. Then what we can say is that for the first mode of vibration, that the wavelength, lambda, that's capital, so lambda is equal to 2 times the length. Okay, because this is half a wavelength, right? If I multiply the length by 2, I would get a full wavelength. Yes? I hope so. Right. For our second harmonic, sorry, our second mode of vibration, I should say, n equals 2. So for our second one, n equals 2. But this already is a full wavelength. and it is length L. So for the second one, we can say that the wavelength lambda is again equal to, just this time, it's L. For the next one, for our third mode of vibration, we would have that n equals 3. In this situation, we have a wavelength and a half. Okay? And that makes life a little bit more complicated, because that would mean that the wavelength is equal to, well, it would be 2/3, wouldn't it? 2 over 3, 2/3 of L. And now we'd like to find a pattern here, but it's not massively easy to see. Until we do this, instead of writing lambda equals L, would it be fair to say that we could write that as 2L over 2? Yeah, I hope so. And instead of writing this as just 2L, we're going to write this as 2L over 1. And what we should see now is that as the harmonic number goes up, or as the mode of vibration number goes up, as n increases, so n goes from mode of vibration 1, n equals 2 for mode of vibration 2, n equals 3 for mode of vibration 3, what we have is we have lambda is 2L over 1, lambda is 2L over 2, lambda is 2 over 3L, but we could certainly write that as 2L over 3 to give us a general rule. And our general rule will look like this. So we copy that and paste it over here, but instead of on the bottom line of having 1, I'm going to put n. And our general rule then is for any stretched string problem, we have that the wavelength that is created, the wavelength of the standing wave that you generate, is going to be 2 times the length of your string that you use divided by the mode of vibration that you are using. That's a pretty important equation. Lambda equals 2L over n for stretched strings. Okay. Right, I think that'll do us for this episode. In the next one, we're going to take a look at, well, what happens if it isn't stretched? What happens if the ends are free to move? What do we do then? Do the same equations apply, and does stuff work? But for now, just a quick recap. What we should understand is that a standing wave is created by one wave that's traveling in one direction and another wave that's traveling in another direction. Okay, when those two waves meet, they superpose, and as a result, you get this wave that looks like it's not traveling at all. It is the superposition of two waves traveling in opposite directions. Now, we need these waves to have the same frequency, we need to have the same wavelength, we need them to travel at pretty much the same speeds, otherwise we're not going to get a standing wave. For the perfect node position, we also need similar amplitudes, okay, so we need the same amplitude as well. So for our last little thing, a little recap, so for standing waves, we have 3 conditions, okay? We have 1, same wavelength. 2, same speed. 3, traveling in opposite directions. Okay, if we do that, we can have standing waves. What we then want is, for a very observable one, for one that we can see readily, we would like 4 same amplitude for easy observation. All right, ladies and gentlemen. Then, once we've got our standing waves set up, there are different types of standing waves you can get. In the situation where we have a stretched string, we have our simplest one, which is a node at one end, a node at the other end, and an antinode in the middle. That is the first mode of vibration. For the second mode of vibration, we introduce a level of complexity. We introduce another node. So we have node at the end, node at this end, and a node in the center, giving us 2 antinodes. And then for our third level of complexity, we would have a node there, a node there, a node there, a node there, for 4 nodes and 3 antinodes. And the next one down would have 4 antinodes, and 5 nodes. Okay, the wavelength that's created for each of these is lambda equals 2L over n for stretch strings. And we'll see the next time that that equation changes when we're looking at ends that are free to move. Now for now, try and keep that all in mind, and don't forget everybody, physics rocks. It's true.